let's consider how to predict the products of a chemical reaction. And we're going to use the modern system of classifying chemical reactions as one of four kinds: simple decompositions, oxidation-reduction, ion swaps, producing a precipitate, and ion swaps that produce water or a similar chemical. We call those an acid-base reaction. Now, what products usually form in a chemical reaction? The answer is the products most often formed are low energy compounds, because energy tends to run downhill in both physics and chemistry. Carbon dioxide and water are often products of chemical reactions. And so if there's carbon and oxygen in the reactants, you very likely will have carbon dioxide in the product. If there's hydrogen and oxygen in the reactants, you'll probably have water as a product. In simple decompositions, carbon dioxide and water are often products as well. In ion swaps, insoluble salts are often produced because they are very low energy compounds. And in acid-base reactions, water, a low energy compound, is almost always produced. So it's always a safe bet to guess on one of these low energy compounds coming from a chemical reaction if the reactants will make it happen. Now, the first type we'll look at is called simple decomposition. Simple decomposition is a process by which some sort of usually crystal or molecule just shakes apart into its constituent parts. There is no transfer of electrons, and so the oxidation states do not change. If there are any ions, they will keep their oxidation states. For example, you can see in calcium carbonate, you can see calcium oxide hiding in that compound. You can see the carbon dioxide hiding in that compound. And so when calcium carbonate is heated, it produces calcium oxide and carbon dioxide. The oxidation numbers have not changed. You can just guess this one, seeing the carbon dioxide is part of the compound. Now the rest of the compound, of course, of the carbonate ion, the rest of the compound is calcium oxide. That is a low energy metal oxide. You can also look at this as a simple decomposition. In a hydrated crystal like calcium chloride dihydrate, you can see water kind of hiding inside the crystal, and so when it's heated, it just breaks up into the anhydrous calcium chloride and molecules of water that come off as steam. Water is a part of the compound. The rest of the compound is a low energy salt. Low energy salt? What in the world is that? Well, remember, when you see a metal and nonmetal coming out of a reaction, they're probably going to end up combined in a compound. And if it's not an oxide, it's probably a salt. And you remember when you study the periodic table that metals become positive ions and nonmetals become negative ions, and they can attract each other to form low energy compounds. The metal becomes a positive ion called a cation. The nonmetal is a negative ion called an anion. So in the dehydration we just saw in the previous slide, they are already coming together as calcium chloride, but without the water molecule. The second type of reaction we'll study is decomposition as an oxidation reduction. This is not a simple shaking apart. If a compound gives off an element as it breaks up, it's an oxidation reduction, because the element has had to either gain or lose electrons in order to turn from an ion or part of a molecule back into a free atom. The oxidation number on the element therefore must change as electrons are moving around. Chlorates are important examples, and we'll show you just one. There are many chlorates. Sodium chlorate, You can look at that and you can see sodium chloride inside it. But the chloride here is a -1, just like it is in all chlorides. In the chlorate, you can see that its oxidation number, because oxygen is -2, the chlorine here has an oxidation number of +5. And that's why this is an oxidation reduction. Moreover, you see an element, oxygen gas, coming off. And so the oxygen has had to have an electron shift in order to become neutral oxygen. So within this compound you see oxygen and the low energy salt sodium chloride, but you also see that the oxidation numbers are changing, and you're not getting off a compound here, you're getting off an element from a compound. So it must be a decomposition, and we see that the products are very predictable, the low energy sodium chloride and the slightly high energy oxygen gas. Now, if electricity is used for a decomposition, then electrons must be moving, and therefore it's an oxidation-reduction reaction. And most of the time you get elements out of it. So if, for instance, you see a compound called sodium chloride or any other chloride, and you see that electricity is passed through the molten compound, and the question is what elements or what is produced from it, you know that sodium and chlorine are going to be produced because the electricity is used to pass through the compound, and electricity means electrons are moving. The sodium ions here, I've just put the plus in parentheses, it doesn't really have a charge in the compound. The sodium has taken back the electrons, and the chloride has lost electrons, giving you neutral sodium atoms and neutral chlorine gas. Combustions are also oxidation reductions. Combustion is burning an oxygen. It's obviously an oxidation because the original meaning of oxidation is burning an oxygen. Low energy compounds that are produced in combustions are the highest oxides of the elements in the substance that's being burned. In a complete combustion, for instance, carbon dioxide is produced. Carbon would be a +4 in carbon dioxide. So here we are with the burning of ethane gas, and this will form again two low energy compounds that can be formed. You see the carbon can combine with oxygen, the hydrogen can combine with oxygen, and that's why you're getting carbon dioxide and water vapor. Now don't forget to balance the equations. That's very important. There's also oxidation reductions that are replacements. These look quite different from combustions. Remember, active metals can replace the ions of less active metals in a solution of a salt. For instance, you may have seen copper react with silver nitrate solution to form silver metal and a blue copper nitrate, copper 2 nitrate solution product. You may have seen magnesium reacting with copper nitrate solution. If you've seen that happen, you ask the question, what's produced? Well, you've got magnesium, an active metal, and the copper 2+ ion. Well, the nitrate, of course, is a spectator ion. So what's produced? Well, the magnesium is an active metal, so it can give away electrons. So it gives 2 electrons to the copper 2+. The electrons, negative, are attracted to the 2+ of the copper in solution. So the copper then turns back into metallic copper, and the magnesium, having lost 2 electrons, turns into magnesium 2+ anion. Those then must be the products, solid copper and magnesium ions in solution. Another kind of replacement that we've run into is different. Active nonmetals can replace the ions of less active nonmetals in a solution, just like the metals can. Usually we're running into this with halogens. chlorine, bromine, and iodine. For instance, if you take chlorine water, chlorine dissolves in water, and you shake it up with, say, potassium iodide solution, you will get iodine, the element, and the chlorine turns into chloride ions. So what's happening is that the chlorine is a more active element, so it steals electrons from the iodide and turns the iodide into iodine and turns itself into chloride ions. Again, the chloride ion is a very low energy thing. So this is how you can replace a nonmetal with another nonmetal. Ion swaps are the fourth type of reaction. And remember, when we do an ion swap, there's kind of an inny-outy going on. We're swapping cations and anions. Acids will start with an H. We know sulfuric acid, H2SO4, hydrochloric acid, HCl. Bases generally end in OH, like sodium hydroxide or calcium hydroxide. Each hydroxide, here in the base, can react with a hydrogen ion from the acid to form water. The cation left behind can combine with the anion left behind to form a dissolved salt. So, for instance, calcium hydroxide reacts with sulfuric acid. We get the swap. The hydroxides react with the hydrogen ions to form water, and the calcium then is left behind as an ion with the sulfate ion to form calcium sulfate, and we can drive the water off and we can recover this calcium sulfate salt. This is an inny-outy ion swap. The other ion swap is the precipitation reaction. These involve two aqueous salts. For instance, sodium chloride reacting with silver nitrate solution. Now you need to know your solubility rules. There is no way to get away from them. So if we look here, the outie here is the sodium and nitrate. And of course we know that sodium compounds are all soluble in water. In fact, nitrates are always soluble in water. So if there's a precipitate, it can't be sodium nitrate. That must mean that the precipitate here would be silver chloride. So when you see this, really the first thing to go for is what is always soluble, and then what's left, if there's a reaction at all, what's left is the precipitate. Then all you have to do is worry about getting the formula of the compound correct. And that means you have to know the charges.